Hi everyone, my name is Nguyen. I'm from SecurityScorecard. Thank you all for coming to my presentation today. And I'm very happy to share with you our recent work to build a system which is scalable and resilient based on ScyllaDB. So let's get started. So here's the agenda for today presentation. At first, I would like to introduce about SecurityScorecard and the main product that we provide to customers. Then I will share some technical challenge that we have while building this product, as well as some recent improvements that I'm proudly to share with you on here. Then we go through the result and lessons that we have learned during the work. So let's get started with security scorecard missions. So this is our missions to make the world a safer place. In fact, we want to help organizations around the world to capture, communicate, and remediate security threats and vulnerabilities to their stakeholders instantly, correctly, and thus um, to make our world a better place for everyone. It sounds interesting, right? But it's also quite general for many of us here, especially for tech people. So let's get a bit more detail into how we're gonna do that. So here at a security scorecard, we evaluate organizations' security profiles using a score called security ratings. These security ratings are very similar to financial credit ratings, as many of you might know, which is we score the security posture of an organization to indicate whether that company is in a good security environment or not. So, for example, if a company with an app score, and then we find out that that company with app score would have about 7.7 percent of 7.7 times of higher chance to be sustaining a data breach compared to those with A score. So here the cybersecurity ratings provide an objective way to monitor the security readiness in an organizations, and it helps to verify the security posture, whether it is improved or improving over the time. At Security Scorecard, we measure the security ratings for over 12 million organizations globally. And this information is very valuable for vendors, risk management, as well as cyber insurance, and those that need to have some assessment of compliance with the security standard. So now you're probably gonna ask like how our security rating score are calculated. In fact, we compute a score via very complicated data pipeline, but you can see here is an abstractions of different modules, which are starting from signal collections, in which our global networks of sensors are deployed across over 50 countries to scan IPs, domains, DNS, and various external data sources to instantly spot threats. And then the result of this will be processed by attribution engine and cyber analytics modules, which we try to associate IPs and domains with all kind of vulnerabilities they might have. And finally, the score engines will compute a rating score for over 10 million scorecard, which is also an organization in our terms. And my team here is responsible for scoring engines in which we compute a score and we provide an efficient way to access this score to other front-end services. And this is where we found some challenge that we need to address. And we're going to go over it now. Here is our scoring architecture before mid of 2022. On the left, you want to see a platform API which receive requests from end users, and then it make further requests to other internal service. One of the service that we have, which is a measurement service, It will query into different data store such as Redis, Aurora, and Presto on top of HDFS to get the requested information that it needs. And on the right side, you see a scoring workflow. It is an enhancement of Airflow, Apache Airflow, and it's responsible for running the job to generate the score of and the measurements and the findings of over 12 million scorecards down to each domains and IP. Why we have this architecture? That's might be the question that you might have. At first, it has been developed quite a few years ago, and it proved that it served our purpose to a certain level. And it is a good architecture as well, because as you can see, we use the right data stores for different purpose, such as Redis, because this is a key value store. It is being used as a key, as an in-memory cache to look up faster. And Aurora, this is a relational database cluster that's with distributed storage, allow us to store huge amount of data across different nodes and runs low latency queries on top of that. And here we also have Presto, which is a SQL engines, general SQL engines running on top of big data data store like HDFS. It helps us to run a complicated SQL query to extract information regarding historical and findings and over a long period of time. So, however, this architecture has several issues that we need to handle, especially when we have more data and more requests over the time. The first issue is that at certain time and for a certain request, there are high latencies in our platforms. As I said in the previous slide, at a certain time during the day, the scoring workflow generates the data and it runs a batch inserts into our data store. And the Aurora cluster, since it consists of one primary master for write requests and several replicas to provide high availability for read requests. But during this time, the replicas are so busy to keep up with the primary one to make sure the data is inserted consistently. And since there was more than 4 billion rows to be inserted within 4 to 5 hours, then these replicas just so busy to handle these requests to make the data consistent, and it caused the response in read requests up to from medium to high latency during that time. Another issue that we have is with Presto query, which is it's one of the issue that I show up here is a query to send to Presto, and it's look for all measurement details from a list of scorecard within a period of time. And the Presto workers, what it needs is it will send a query and scan all the block files in HDFS during set time and filter those records that meets the requirements. It worked well under the low workload, but when the request volume is getting larger, as well as we collect data over time, we have more signals, we have more data need to associate with each scorecard. We see that the Presto workers behave quite badly and it stopped working during certain time because under the high workload, the latencies get up to 10 seconds or more, up to minutes. And not to mention, it's also impact the whole platform to serve other requests. So that is a high latency issue. And the next issue that we have is the scalability. In particular, we reach the vertical scalability hard limit of Redis, which is in particular AWS Elastic Cache, because it's the largest instance we can get, which is around 400 gigabyte in memory cache to hold up to about 12 million scorecard, and we cannot go further than that. So at that time, we try different solutions that use a Redis cluster to be able to set up a multiple instance so that it work together to provide a larger memory capacities. However, there's an issue that the Redis clients, the one that's running the query, Redis query from our service, need to know exactly what Redis instance is, where it is, and what it is to send the query to. And at that time, we found out that only Redis cluster, which is a Python driver, that would be able to do so. But since we have different service running in Java, in Node.js, and in order to make it work with Redis cluster, we have to implement a custom driver on top of that, which is also a lot of work for us. And here's another issue that's related to our business requirement, in which we want the organizations to be able to remediate findings so that the security ratings score would be improved as quickly as possible. This update is not be able to do because the HDFS data store, which is the data store running behind the Presto query, is a write one and read many times of block files. So all the data ingestion into Presto HDFS need to go through scoring workflow, and it's caused the delay to update the score up to 3 days. And that makes our customer unhappy, and it drives us to seek a better solution. And this is our last issue that we encounter, which is related to software maintenance. We have about 50 internal services. They are implemented in different tech stack, such as Java, Node.js, Python, Go, you name it. And these service could access the data store on their own directly. So they have to handle different type of query, SQL query, Redis query on their own, and also have to handle it very efficiently and effectively. So if we change any things on the database schema, or we upgrade the database, all these services also need to be upgraded, which is causing a lot of technical depth to our system. So that is the issue that we find out, and that's why we have to go further and seek for better solutions. And we find out that when we migrate our data to ScyllaDB, that's turned out to help us to solve all the issue that we have. So let me show you why. So this is the new architecture that we have since August 24, 2022. As you can see, this new architecture is very simple. Is more simpler. It's simpler, and which is we use a Scylla Cloud cluster to replace Redis and Aurora. And instead of having HDFS, we use S3, AWS S3, to store all historical details. And here we also introduce a service called, which is work as a data gateway. This service called Scoring API to handle requests to different data store. So now you might ask why this architecture can address the previous issue that we mentioned. So here comes the answer. So about the latencies, first of all, this architecture helps us to deliver low latency and high throughput to other service. So let's consider the same query as we had before, in which we get the detail of scorecard detail of a list of scorecard given within a period of time. And based on that query, we have designed an optimal ScyllaDB schema to allow us quickly access the data that we need based on the primary key. And so imagine that upon receive a request from Scoring API, a Scylla coordinator node could know exactly where the replication nodes containing such data, and it just need to send those requests to these replicas. And from there, the replicas just get it and send it back. One more thing is we also have our Scoring API to implement it in a way that it supports highly parallel processing tasks. So for example, in the query that you're looking at, in which there's a where condition where UUID of a company in a list. So that list might be really big, like like thousands and up to 100,000 scorecard there. And it is a limitation of ScyllaDB, in particular SQL, to handle that long list. So we have to provide the parallel processing by dividing that list into smaller sublists, and then we send the request in parallel and aggregate the result before returning back to the other service. And here also one noticeable improvement is that during the peak time of write workload into Scylla, the read throughput is still very good, and with low latency access as well. This is because the eventually consistent features provided by ScyllaDB, which allow read consistency, can be achieved even given a certain level of write consistency that we have in the request. So the second improvement is about scalability, in which we can add more nodes into our Scylla clusters, cloud cluster, depending on the needs. And also we can, and by doing that, we overcome the limits of storage, of in-memory storage that we have with Redis. Also, we have the scalability in the scoring API, because it is deployed as an ECS service, and we can add as many more instances as we need to serve the request faster. And this is the last improvement that we can share, which is now on the other service, instead of accessing the data store directly, it just send a REST query, REST API query to scoring API, regardless of the tech stack. And now the scoring API work as a gateway for data accessing. It will direct the request to the right place depending on the use cases, such as if the request need a low latencies response, it go to Scylla. Otherwise, if it is like high latency tolerance for historical data, it go to Presto S3. And here it also can work as a data fault tolerance fallback, because if there's any error in ScyllaDB, then scoring API will send the request to Presto S3 to get the data that they need. And also, now the customer can quickly remediate the security finding, because it just need to send an upsert request to ScyllaDB, and thus it's also satisfy our business requirements. And here's the result. So in August 24 of 2020, we switched over from old architecture to the new one. And as you can see, the latency is immediately significantly decreased up to 90%, or to almost to all on endpoints that we have. And then we have like 80% incidents less compared to the time that we have Presto and Aura there. And also, we have saved over 1 million infrastructure costs per year when we switch over to Scylla DB, because now we don't have to maintain several cluster of AWS EMR and Aura, which is have a lot of costs over there. And also, we have reduced the time to do the scoring up to 30%, because now when we write to Scylla, it's much faster compared to when we write the data to Presto and Aura. And last but not least, it's improved a lot on the customer experience. Everyone's surprised how fast it is, and customer happy is what makes us happy as well. So this is the lessons that we have. We learned that why working with ScyllaDB, designing the schema is one of the very important things. It need to be it need to be done with cautious, And especially from what we have done in the past, we check the access pattern from the query that we have, and then we derive the schema based on that. We know what should be in the primary key, in particular, what could be a partition key, what will be the cluster key, and also the time to leave of the data that we expect in ScyllaDB. And the second lesson that we learn is we should leave the request of high latency, tolerance, and historical data access to OLAP engines such as Presto or Athena, because it's where desired. They are desired for that purpose, not for user-facing requests. So on top of that, we can do asynchronous processing to generate the reports and send a signal, send the notifications to the platform. And finally, we should have a data controller, which is in this case a scoring API in our architecture that need to be so that it can runs parallel tasks. And then it's also tackle certain cases that SQL query cannot handle, such as join and select in query that's supported in normal SQL, but not in SQL. And that's component is important to redirect the request to different data store, playing as a data gateway, and control the rate limit to the data, working as a fault tolerance or something like that. So that's really important to have that data controller in your architecture as well. So that's all for my presentation. Thank you for listening.